They are orthogonal, assuming that they are orthogonal to each other. So we have B1 and B2. We have two vectors B1 and B2. They are orthogonal to each other. And this is my original vector R. Right? So now, how do I make sure that R, how do I make sure that R will be, I can define R in terms of these two vectors, these two basis vectors, B1 and B2. So I can take the idea of projection and say that this could be projected on, I just want to project on B1, and I can project here. So I can project this vector throwing a light on this direction, I can also project throwing a light from this direction. That means what will happen is this vector will cast a shadow here. Let me use a different color for that. So the R shadow will be on this. That means this R will come back here. So this is the projection vector. And when you when you project R from this side, it will project onto this. So what I'm essentially doing is I am projecting this R onto B1 and B2. Fine? So now if you look at B1 and B2 and then if you try to add, let's try to write that. Let's say first projection, what we did is, let's call this as RE. Because we are looking at in terms of the E projection, so E basis vector. So we are starting with RE, so that means we are taking this vector in RE, the values on RE, and then we are projecting it onto B1 and B2. So if you do that, let's try. Okay, let's try to say and let's give some numbers so that you can easily verify. So let's go back and then I can give you some numbers here. Let's say this would be a basis vector, so it would be 1 and 0. This would be 0 and 1. And then let's call this as 2 and 1. And let's call this as minus, I think I made a mistake. So this should be 0 and 1, and this should be B2, should be minus 2 and 4. So we can check and verify. So I have defined two basis vector, E1 which has the coordinate 1 and 0, E2 has 0, 1, and you have B basis vector in some other space. Let's call B1 and B2. So let's give that basis vector as, that is 2 and 1 and minus 2 and 4. But in that space, it's actually 1 and 0 and 0 and 1. But in our space, it is actually 2, 1, minus 2 and 4. Now if you can check and verify that, B1 dotted with B2 will give you 0, so that means these two vectors are orthogonal to each other. So let's define what is RE. RE would now be, let's give some vector, let's say 3 and 4. Now using this knowledge, if I do a dot product of this, what do I get? So what we get is, when you project here, so this will give you 2 times of B1, and this would be half of B2. So okay, I'm just writing out of scale. So what I'm trying to do here is, let me show you what I'm doing. This is the projection of RE on B1, and this is the projection of RE on B2. Okay. Now when you do that, what you get is you get 2 times of B1, so that's 2 times of 2 and 1, and then you take the second projection vector, so that's your RE times of B2 over B2 dotted with B2 itself. So you get half of B2, so that's half of B2, so what you get is half of minus 2 and 4. And now this is nothing but RE Now you can check and verify that RE was nothing but the projection of first projection added with the second projection. So the first projection was 4, 2, and the second projection was -1 and 2, and what you got is 3 and 4. Indeed, this is what you got. So with a simple projection matrix, you can project on from one space to another space. Now, what's really happening is, so irrespective of the coordinate system, the vector RE could be using the projection. I can define and I can operate all my addition, scalar multiple. I can do whatever the operation we had when it was there in the E1 and E2 basis vector. So it holds good. Even if you change the base, the vector has no influence on that. So we could do the same thing for RD, but I just don't want to do that math. But I just want to show you that it would end up in 2 and 1/2. So that was indeed that was indeed what you got. So it's 2 and 1/2. That was your basis vector. So all you have to do is just reverse transform this. You should be able to get this. So the whole takeaway from this, sorry, I think, am I audible? There was one phone call which I got. I hope I'm audible, right? Okay, sorry. Otherwise, I feel that my neural network is not training properly. It is just again going out of the space. So I just want all of you to be in my space so that you appreciate the concepts which are being laid out here. Okay, the whole takeaway here is simple. So if you look at vector R. If you look at the vector R here, that has no effect, or I would say that is independent of basis. So that means there is nothing like even if you change the base, even if you change the coordinate system, basis in the sense it is pretty simple. So I just want to tell you in a very easy way that don't get confused that base, people talk about basis as a different way, but what I understood or what I can make you understand is simple. In simple layman term, bases are nothing but the coordinate system which you are laying down for that space. Now we have seen that we moved, if you look at here, we moved from one space that was, if I just try to write it in a different color, okay, let me use this color. So this was your E1, this was your E1, this was your E2. So that was your original space. You had a vector in the original space, E1 and E2. That means I had a coordinate system, E1 and E2, and I had a vector in my space. Now what I'm doing is I'm trying to make sure that even if I do change my coordinate system, my vector position is not, I can do all the operations which I can do by simply projecting those simply projecting the vector onto that space. So this is the basic fundamental idea about the approximation which Dr. Shiva was talking to you in the early morning. So he said that when you are looking at the least square approximation or the approximation in general for any machine learning problems, so we always have no solution. The reason is because we don't know the hyperplanes which we are trying to fit for a simple non-linear separable problem. I think if I'm going back to the Nagushin's class where he was trying to talk about the hyperplanes, and then he was trying to talk about the classification of cat and dogs. So where you could linearly separate. So if you are looking at a three-dimensional, then I just need a simple plane which could cut that cube into two halves. One half could be the class 1 and the other half could be the another class. So here, in a general sense, we actually don't get that curve, or I mean, because we are looking at non-linearity, we don't get to know the functionality of that curve. The reason is because based on this, we could see that when you do the transformation to a vector to make sure that it lands up on that space, you are basically using a projection. So what I did here is simple. I projected a vector which was not there in my space. To make sure that the vector is there in my space, I projected, I did all this math, and I made sure that I got a solution. So the solution is one way, the solution could be two way. So this all depends on the next topic which we are looking at, that is inverse and the determinant of that. So let me, let's try to, let's try to wrap up this part at least, so that you could appreciate the next concepts which you are looking at. So so the key concepts which we are looking at, the idea is the questions which are posed. I'm sorry, the question which is posed is what do we do? So the question is, what defines the dimension of a space now? So what is the dimension of a space? Now, previous speakers have already talked about dimensions, but I just want to give you a crisp and the very easy way to remember is that we are trying to find the collection is a set of independent vectors. It's a set of independent vectors. So I would say this is V1, V2, V3 and all up to Vk. So I would say that all these vectors which you're looking at from V1, V2 up to Vk, all these vectors are independent. So that means I'm trying to find a rank of a matrix, and if the rank of matrix, let's say if my space is 2 dimensions, and if my rank of matrix would give me 2 independent vectors, then those two would be called as the bases. So I would say B1 and B2, these are the 2 bases, and these 2 are the 2 bases which will be used later to fill up the entire space. So those 2 vectors, I can use a linear combination of those 2 vectors that could fill up my entire space. So the next question which we generally ask is why transformation? Why are we looking at transformations? Why transformation? One way to look at transformation is you could think of transformation in multiple ways. One would be to, let's say I have a vector here, let's say I have a vector here, vector v. Now what I want to do is I just want this vector to move a certain distance and align here. So vector v prime. So vector v moved from, okay, let's not call a dimension. So this is a vector v moved from here to here. Now what I essentially did was a mapping which moved from here to here. So this would help you in all your gaming applications where you want to move an object from one place to another place, and then want to do the reverse operation, let's say undo, and you want, let's say you're playing a game and you hit a dead end, let's say you crash, and you want to come back and restore from where you want. So you do, this is your transformation T, and now when you do a reverse transformation, I would get from V prime to V, right? So this is my reverse transformation. So these are a few applications which use transformation. So this is one application, like when you're looking at computer graphics, when you're trying to play a game and you want to identify where the next position would land up. Right, so that's one. You could also look at recognizing face, like maybe in a face detection problem, or face recognition problem in general. So we look at all these the features which are taken, that eye, distance between the eye, hue, mouth, the color, or maybe then you don't want to take the entire face, but you want to take a few of those, few of them. So let's say if I have a face here and bad at drawing, let's say this is a happy face. So instead of taking all these minute little pixels, if you don't understand this jargon, so it's okay it's okay to understand this part. Just try to understand that pixel is the smallest quantity in an image which you can represent. So I'm just trying to draw so that I don't make this image a very bad shape. So I have, these are the smallest element of an image. So the key way to do that would be to pick up all of them and align it in a matrix. So that means I have P1, pixel 1, pixel 2, pixel 3, and it just goes on up to pixel M. So this could be given to your neural network model. You get the output, that's Y predicted, right, tilde. And then what you do is you go through the optimization. Let's say you give a feedback to this and you try to optimize and then see that Y tilde is very close to Y. So this Y is the actual. You know the actual, but what you do is you tend to move towards that. So that's the basic about neural networks, linear, the machine learning or deep learning in general. Now, in a sense, instead of if you do this, if you take all these pixels naturally, and if you try to plot them using a scatter plot, so these are my data points. Now, what will happen is these data points would now be somewhere scattered somewhere in the space. Now, we don't have a way of measuring how close or how far is these two. So I cannot find any relation between these two and these two. So can we say that these two, can we say that, let's say this is A and this is B, vector B, then this is C. Can we say that A and B, let's say that A is very close, approximately close to B. I would say close to B, close to B when compared to A to C. So if you are relating these two, I cannot say, the reason is because they are sparse. So what will happen is, when you take the dimension of your space to be large, that means your dimensions are large, it's because you have taken more information and your dimension naturally increases. And this will also have a bad effect, and yesterday I think Nabhushan sir talked about curves of dimensionality. Curves of dimensionality. And what will happen is the more information you have, the more you have trouble, because you don't know, do I have a copy of the same information, or do I have do I have redundant information? So what we are looking at in terms of transformation, in the sense, I am trying to make sure that this whole higher dimensional object, or this whole higher dimensional space, let's say this is my high dimensional space, let's say beyond, let's say n, And what I want to do is I do mapping and I want to transform this into some k-dimensional, very, very less dimensional space where k is very less compared to n. So in a sense, what you are doing is you are trying to do some kind of a transformation where you are trying to change the coordinate system. So I believe that we appreciate now that we have some points here in this space. This is my original space. And now I have some set of points which is in my transform space. So this is your original, this is my original space, and this is my transform or maybe some space, so I would say transform space. Correct? So now the whole idea is you're trying to do some kind of a mapping, that means you're doing some kind of a transformation, and I'm stressing more often that this transformation is linear. So I'm trying to do some kind of a linear transformation. So in order to make sure I do a transformation, because there are some points here which are not independent. So that means maybe this guy over here, this guy over here, this guy over here, maybe these guys are some linear combination of some vector. So now I would say that this may be a copy of my, in essence what I'm trying to say is that if you add up this guy and this guy, if you do some kind of scalar multiple and then add up these two, you will end up here. Correct? So now there's a point of trying to understand that this linear transformation would help us in trying to do some kind of reduction in the dimensions, which the next speakers are going to talk more about it. I don't want to talk about it, but I just want to give you an essence that we are dealing with the spaces of these vectors, a collection of these vectors, and I assume that all these vectors are essential to define my object. But it happened that when you tried to model it, you couldn't get any answer for that because there are a lot of other redundant details which you are trying to give in. So it's as good as you're trying to give more information and you're confusing the model, you're confusing the audience, or you're confusing the customer. So in that sense, we are trying to reduce, that means we are trying to make sure that through some kind of transformation and a special kind of vector, which will be told in the next session, that we try to do a transformation and do a mapping. Now my whole idea is, can we map from this vector, this space, can I map from this space to this space? So let's say this is my O space to T space. So that means this is my original space, and can I do a transformation to this space? Now what will happen is, all of you, most of you would have a hands-on experience on working with a little bit about machine learning. Maybe you would have done it. Even if you have not done it, don't worry, this wouldn't be a jargon for you. Now what we are trying to do is, we are trying to map the only vectors which are discriminative about the object which you are trying to describe. So that means these vectors which you are looking at, right? So I could now say that I need only these vectors, and these vectors are called the basis. And when I say basis, they are independent. They are independent vectors. So these independent vectors, when you do a transformation of these, when you do a map from one space to another space, you should be able to get the solution. So the whole idea of transformation, think of transformation as nothing but projection. You are trying to project from one space to another space. So this is one-way projection. Correct? So maybe what you have done is you have tried to project, you have tried to take an object. In this case, what you have done is you, if I go up, you took an image of a happy face of a person, and then what you did was you tried to represent that as instead of having a m vector, dimensional vector, you just represented with some k-dimensional vectors. So let's say k1, k2, up to some kp. So there are k-dimensional vectors, and these are very small compared to n. So what essentially we are doing is we are trying to remove those redundant vectors, which are linear combination of those, which are holding you to, which are making your vectors, the solutions to go out of the space. Now, how do we do it? We try to project those vectors onto this space and make sure that you have a solution. Right? So that's your transformation. So, so this is one part of transformation. I mean, this is one part. So from here, I just want to quickly try to tell you about the other things which are there, called the determinant and inverses. So we have been all reading this determinant and inverses from our school time, but nobody taught us why and what is the geometrical interpretation of this determinant. So, so the question which we are trying to pose is what if what if it's, here, what if the matrix, what you have looked at, that is your matrix of feature vectors, or the matrix, has dependent vectors. You have the dependent vectors. So you use those methods to solve them. So let's try to look at determinant and matrices, and what does determinant geometrically would help us. Let's look at a simple example of a matrix. I would say you start with A, 0 and 0B. Let's say you have a matrix here. How do I represent this? Let's try to say that this is my E1, this is my E2. I'm just using the same Cartesian coordinate system, and these two are the basis vector for them. Now what I'm doing is I'm saying that you don't change anything on the E2, but you need to scale up E1 in this direction. So you go A times of E2, right? So I will say that it is E1 prime. Fine. So, and if you look at this vector, now it is saying that you don't change anything in this E1, but you scale up in this direction by d times. So this is E2 prime. And what essentially has done is I moved up my space from a square here to A times of this and b times of this. And ultimately what I've done is I'm just trying to fill up the space, and the area of this space, you all know it's A times of b. That's the area. So this is called the determinant. So a determinant is going to help us in trying to identify the factor of by which you are trying to scale space. So you could scale space, now you could scale space by A times of B, but now if I have, suppose if I have, let's say, let's take another case, let's say another matrix, suppose if I have A, B, and then say 0B. Now what's really happening here is I have E1, E2. So this is my E1, this is my E2, and now this goes up A times, that is E2 prime, and that's E1 prime as it is, right? So this is my E1 prime. So I didn't change anything here, but it's changed from B and D. So instead of a square, what I've done is from a square space, I have been moving to a parallelogram. Okay. So now you could verify this, that this is A, this is B, but you get the same area as AD, right? So similarly, if I change, if I have a matrix that is A, B, C, and D, if I change for everything, then what do I get here is from E1, E2, and so you are changing E2 here, which will be E2 prime in terms of A and B, and then E1 will be changed to E1 prime here, and what do I get would be another space called a parallelogram. And if you want to find the area of this parallelogram, I don't want to do that, but the area of this parallelogram is given by A times of B minus B times of C. You can verify. So because of lack of time, I don't want to get into the details about that. So how it is related to the inverse? So we have seen that we have a matrix A, B, C, and D. And if I take an inverse of that, so I just flip A minus B, and I just flip this, what do I get? If you multiply, what do I get? So it's A times of B, then minus B times of C, right? So it's going a little funny. So A times of B. So this is something that what we got. So what is this? This is my area. That is let's say this is a matrix A, and I'm trying to do a dot product of that to an inverse of that. So let's see what happens. So you got A D minus BC, and then when you try to do a dot product of this one and then this one, so this AD minus AD, so this goes to 0, and again CD minus CD minus CD, where this goes to 0, and then we should be able to get, this is AD minus BC. So now we got a nice equation for, I could just factor out 1 over AD minus BC. What we got is a very nice identity matrix, right? So that's the determinant. So we all know that if you multiply A times of its inverse, so we get the identity matrix, but I'm just showing you with respect to finding out the determinant. So what essentially we are doing is, we are actually working with the space. It's a change, I'm sorry. So we are working with the scaling of those spaces. This will give me the determinant. So determinant is going to give you a lot of information.
Yes, sir.
Sorry, I think participant, can you mute to yourself? Okay, thank you. So some observation which we are making from here is the determinant defines the amount of space, the amount that.
Excuse me, sir. Screen is not visible.
Fine. Can you come again?
Not visible, sir. Screen is not visible.
Oh. When is that? From when? Is it now? Okay, fine. I'll just see. I think I'll just see. Yeah, now?
Okay, sir.
Yeah. So was this clear? Was this clear? The determinant part was clear to all of you? Was it there? Was the screen there and then it got abruptly ended? Okay, thank you. So, so one observation which we make is when we do the determinant, we define the amount of determine the amount that scales the space. We are trying to say that we define the amount that scales the space. So we are trying to say how much is that scaling is doing. So we would say that this is my, you know, I mean, I can, if you know how much you are scaling, that means you know how much you are enlarging. I can do the reverse operation and come back to the same you know, place where I was. So let's say this was your A, and let's say this was D minus B minus C and A times of A, D minus B, C. So this one is trying to show you. This one is trying to show you the scaling. That's the reverse part. So this undoing of the scaling will help us to move from one space to another space. So the whole idea or the problem which we are trying to, maybe you can look at one application of the problem that will make this life easier. So you could just say that you have two vectors E1, E2, and I have E1 prime, and it could just scale into this direction. I mean, I can just go. So this is one dimension. So what could be your vector? So you have 1, 2, 1, 2. So what does it mean? What does it mean? So how does it relate to my the previous example which we looked at, linear dependency and independency? If you clearly observe the first column and if you look at the second column, they all are same. So it's just the copy of first column. So second column is a copy of second vector is a copy of the first one, and then it is enlarged by 2. So that means you have 1, 1 and you scale it by 2. So I have 1 and 1. So if you look at 1 and 1 here, so it's not gone to scale, but this is E1 here. That's your E1, right? So E1 is a vector, and this is 1 and 1. And if I have another vector that scales, so this would be scaling by this factor. This is 2. This is 2, right? So this is where you get E2, so that is 2 times of 1 and 1. Correct? So that's what you're getting. So this is where the linear dependency and independency have come into picture. So that means we are looking, so you can arguably see that these two vectors are not the basis, and these two vectors have dependencies. So what does it mean? It means that one vector is dependent on the other vector. So you can see that if this condition exists, how do you check? How do you check with respect to determinants? How can we verify? So one observation which we can do is quickly can we find the determinant of this? So what's the determinant of this? So it's 2 minus or 2. This is A, B, C and D. So AB minus BC. So this gives you 0. So what does it mean? It means that there is no space, there is no enlargement of this space. It's just moving in that direction. I didn't get a space. That means the space is null. Null. So this is a clear interpretation of one-way transformation. So you have one object, one vector, and you take that vector and you do a transformation matrix, and that transformation matrix changes the space to another space, and you are there in that space. Now, to be very precise, so I am there in this space, and this is another space. Now what you did was you tried to map because we were working here, we were very happy, but suddenly we wanted to make some friends over this space because we know that these are, this would help me to solve my problem, because I found that none of my colleagues here, none of my friends here are able to solve my problem. I just want a help. I call a help from T. So this T is a function which will take me and then map it to somebody else who's there in this space, right? So this is your transformation. So what you did now is you transformed from one space to another space, but now it so happened that there is no way to return back. Why there's no return back is because you can't find an inverse. Because the determinant is 0, there is no inverse. No inverse. So since there is no inverse, so this would now, I would now say that these vectors over here have some kind of redundancy. They have some kind of redundancy. So this is the reason why you have a lot of vectors, and these vectors, even though you have a lot of features, most of them, they come back to me. So many of my students will come back to me and they say, I have a lot of features, I have taken plenty of features, but now it's not working well it's not working well to the problem. The accuracy is low. I will quickly tell them to look at, did you do a sanity check on trying to figure out whether one feature is having any relation with the other feature. If that is the case, then it's not going to add any value to your model. That means it's trying to memorize, it's trying to learn the same thing in a different form. So this is the big problem of machine learning. So the big problem of machine learning is overfitting. So this overfitting comes in because you are feeding in too much of data. So it's as good as or we like all or another. And if you go on occasion, she tries to make you eat whatever she has prepared. It's because of the love. So sometimes you can't digest that much. So that's overfitting. So you need to make sure that your model works properly. So the whole idea, which I laid out from the session 1 and session 2, are totally interlinked. So quickly, I'll just wrap up this session and then we'll do a summary and then we can take some questions. So this is why we look at a transformation. So I can. Now what you've done is you got what you have got is you got a solution, but that solution is there with somebody else. You got a solution, but that solution is in this space. But how do how do I know that we got a solution? I need to do some kind of a reverse mapping. Okay. So that reverse mapping is what we are looking at here. So that is my T inverse. So if you have a linearly dependent vector or a matrix like this, or if you look at, you don't have you have a linearly dependent vectors, then you have only one way. That means you move from here to here and you're done. And you're saying that I got a solution, and you are just you're just happy with that. But now when you got a solution, but you want to verify, are these really true or are these fake fictitious results of the solution? So you want to reverse map it back to my original space. So in that case, I cannot do if my determinant of that matrix is 0. So that means I don't have inverse and I'll not be able to map it back to the same space. So it's a word of caution that if you are working with spaces, changing between spaces, then you need to be very sure whether you want to have a reverse mapping, or you want a one-way kind of transformation. So I had few more things to be told. That is, how do you really transform? I mean, I just told you this T and T transform. T and T inverse as a transformation matrix. But I had a lot of, because of the scarcity, because of the time, I don't want to get into this, but I can share you the slides and the notes which I prepared. It will help you to understand better the T and T inverse. So how to get this T in the sense, what is the transformation matrix you define so that I land up in the same, I land up in different space, and how do you create this T inverse so that I come back to my original position. So this is about change of basis, change of space, change of basis, or change of basis vector in space, right? So I stop here. I know that it went on very fast, and some of you had a lot of issues with the audio, and then sometimes we had to the sharing was not proper. But I think I have made a humble presentation to all of you to make sure that you appreciate linear algebra. The whole idea, in a sense, is to give you the experience which we had when we were working towards a research problem, and we all thought about in this direction, and now we are trying to appreciate. So I know that most of the stuffs are being covered here are actually being taught in our schooling, but there is no connection between these things. So we know vectors, we know scalar, we know dot product, we know length, we know, some of them would be like, we didn't know maybe independent or dependent vector basis. Maybe there are some funny names which people have given. But in the essence, what we have done is we have tried to understand the relation between each of them with respect to machine learning. So from now onwards, you shouldn't feel taken away looking at any of the machine learning models, and you should not feel that I don't know, and I still feel that machine learning or the neural network in general is a black box. I don't think it as a black box now. I know what is happening inside when I open it, and I know each and every details. So thank you very much for your patient listening, and for all these hiccups. And then if you have any suggestions and feedback, so feedback forms are already given yesterday. If it's not received, I will just post it on the WhatsApp chat. So maybe you can do it after 4:30. I'm open to question. If you have any questions regarding this, I can take it now. So any questions on this? Okay, so there's, I know, because I tried my best to give you a sense, but I know that this is this whole one week or one session is really not enough to tell you all the details. But we'll make sure that these slides and these notes, whatever we have written now, and the videos would be shared to you on the YouTube, and we'll make sure that the questions regarding what is the textbooks and which are the links to refer to would be shared to you. So if you have, if nothing is there, nobody has a doubt, then we'll end the session. Thank you very much. And we'll see you tomorrow. Tomorrow there is a session on optimization, statistics and optimization by Dr. Nirmal Sancheti. He is the Chief Operating Officer and he owns a company in Aldo Embedded System. So he develops applications and the products. So you'll be hearing from him about the statistical point of whatever we looked at. Now I really gave you an essence of what is vector and what those vectors are there in the space. Dr. Shiva actually told you about how you can use those vectors and use the idea about calculus to find those small bit of tiny bit of rate of change to work with your back propagation and the neural networks in general. And now Dr. Sancheti will be talking more about statistics. That means he talks more about how you look at those data points from a distribution and how to know that whatever the output I'm getting is really the one which I'm actually feeding in from the input. So we are looking at the statistics and the optimizations. So if I'm not right. So thank you very much for today. We'll all meet tomorrow morning at 9:30 sharp.